Unit 20, Electrochem, pages 279 to 288, and we are going to focus on balancing redox reactions. So there's two parts to a redox reaction, the oxidation part of the process and the reduction part of the process. Reduction is a process where electrons are gained. So remember, gain electrons reduction equals GR. Oxidation is the process where electrons are lost. So remember, lose electrons, oxidation is LEO. So you can remember LEO goes GR to try and recall these two definitions. So notice this reaction, and we have a zinc here that has an oxidation state of 0, and on the right side the zinc has an oxidation state of +2. So notice that the oxidation state increased or became more positive, which indicates that electrons were lost, and therefore this is where loss of electrons is oxidation. So the zinc goes through the process of oxidation. That's going to make zinc known as the reducing agent. So this goes through oxidation, and it is known as the reducing agent. The hydrogen is a +1 here, but then becomes 0 on the right side. So because the oxidation number decreased from +1 to 0, or because the oxidation state became more negative, then the process of reduction occurs. And so the hydrogen goes through the process of reduction, which makes it the oxidizing agent. An oxidation process requires a reduction process. The oxidizing agent is a reactant that assists oxidation to occur by itself undergoing reduction. The reducing agent is a reactant that assists reduction to occur by itself being oxidized. So whatever you identify as going through the process of oxidation is going to be the reducing agent, and whatever you identify as going through the process of reduction would be called the oxidizing agent. Example 20.91. In the following reaction, assign the oxidation numbers, identify what is being oxidized, what is being reduced, and what is the oxidizing agent and what is the reducing agent. Oxygen is going to be typically labeled with a -2. And so 2 times 5 is a -10 overall, which means I need the iodine to be a +10 overall. There are 2 of them, so each iodine must be a +5. 5 times 2 is +10, -2 times 5 is -10. Here, note that there's a coefficient that has nothing to do with your oxidation states. Oxygen by itself will typically be a -2, and to balance that, the carbon must be a +2. On the right side, this is an iodine as a diatomic, and therefore it is neutral, or 0. And then here, ignoring the coefficient, oxygen will get a -2. 2 times 2 is -4, and so to balance that, the carbon must be a +4. +4 and -4 make this a total of 0 because it's a neutral compound. Now let's look at what has changed. Notice that oxygen remained -2 the entire time. -2, -2, -2. It never changed. So it's not going to be something of interest. Iodine went from +5 on this side to a 0 on the right-hand side. So because it reduced in value, the +5 reduced to 0, this is the reduction part of the reaction. That means that I2O5 is the oxidizing agent. Notice the carbon went from +2 on the left to +4 on the right. So because the oxidation number increased from 2 to 4 or became more positive, this is the oxidation part of the reaction, which means the CO is the reducing agent. So we're going to use what's called half-cell reactions in order to balance redox reactions. Half-cell reactions are a way to write a redox reaction as 2 separate reactions, one for oxidation and the other for reduction. Half-cell reactions look like this. The reduced species plus electrons is going to yield the product. So notice the electrons are being gained on the left side. Gain electrons. They'll be on the reactant side. The oxidized species yields the product plus electrons. So notice electrons are found as a product, which means they are being lost. Losing electrons is oxidation. The electrons are lost on the product side. So for the reaction we just looked at, I2O5 plus 5CO yields I2 and 5CO2. We can deduce the half-cell reactions as follows. So here, the I2O5 reduced to I20, and so I'm going to write I2O5 plus 5 minus 2. Notice that the plus 5 is a larger or higher oxidation number than 0. And so as a trick, you're always going to add electrons to the higher oxidation number. So I'm going to put plus electrons yields, and we're going to yield the I20. So I2O5 with these oxidation states is going to yield I20. And the electrons are on this side. They're being gained because gain electrons is reduction. So they should be on the reactant side. Then I'm going to write my 5CO. I'm going to write my plus 2 minus 2. And in this case, plus 4 is the larger oxidation state. So I'm going to add electrons to the right side of the equation. So I'm going to put my arrow and then put 5CO2 plus 4 minus 2 plus some number of electrons. So notice that we had a difference of 5 to 0. So that means a total of 5 electrons were transferred between this iodine to this iodine, or 5 electrons were gained. However, because I'm dealing with 2 iodines on both sides, I'm going to have to say 5 times this 2 equals 10 electrons total that are gained. So I took the difference between plus 5 and 0, which is 5, and then I multiplied it times the quantity of iodines, which is 2. 5 times 2 gives me this 10. Down here, I'm going to see the difference between carbon plus 2 and carbon plus 4 is a difference of 2 electrons. So 2 electrons have been transferred, and then times 5 carbons on both sides. Notice I'm using the coefficient. And so 2 times 5 is equal to 10 electrons transferred as well here. So notice these two values are equal, and they should be when the equation is fully balanced. Now let's actually get to balancing a redox reaction. It requires a specific procedure that depends on whether the reaction takes place in acidic or basic solution. So we must balance the electrons first, which requires assigning oxidation numbers, writing half-cell reactions, and the atoms being oxidized and reduced must be balanced. Ignore the other atoms. Then we're going to add hydrogen and water in acidic solution to balance the hydrogen and oxygen atoms in the net ionic equation. We're going to add hydroxides and waters in a basic solution to balance the hydrogen and oxygens in the net ionic equation. This is done by first adding hydrogen to balance the hydrogen atoms, then adding the hydroxide to each side to neutralize the hydrogen and convert them to water. So example 20.92, let's balance the following redox reaction that takes place in acidic solution. So I'll start by assigning the oxidation states. This should be an overall -2 charge total. So if each oxygen is -2, 2 times 7 is -14, which means this has to be plus 12, which makes each of these chromiums plus 6, because 6 times 2 is positive 12, and positive 12 with a -14 equals that -2 overall charge. So we have a plus 6 and a minus 2. Here we're being told the oxidation state of the chlorine is -1. So I'll just write a -1 up here. Here we're being told the oxidation state is a plus 3, and I'm just going to leave it as it is. And here, because that's a diatomic and it's alone, it's neutral, and so it has a charge of 0. Now let's look for changes. We have chromium, which changed from plus 6 on the left to plus 3 on the right-hand side. Notice that the value reduced. So because plus 6 reduced to plus 3, this is the reduction part of the reaction. And so when I write the half reaction here, and I'm going to gain electrons, so add electrons to the left side, yields my Cr3+ on the right-hand side. Okay, now I'm going to see that my chlorine went from -1 to 0. So because -1 increased up to 0, that makes this the oxidation part of the reaction. And so my Leo, lose electrons, means the electrons are a product. Now that I have written my half reactions, I need to balance the number of electrons. Well, first I need to know how many have been lost or gained. So you see how we have Cr2? That 2 there means that I need 2 chromiums on the right side as well. So now that I have 2 of each, I'm going to find the difference between plus 6 and plus 3, which is a difference of 3. 3 times 2 chromiums equals 6 electrons transferred. Here, because there's a 2 subscript there, that means I need to balance this by putting a 2 coefficient here. Now, there's a difference of, from -1 to 0, a difference of 1, and 1 times 2 chlorines equals a 2 electron loss. So, because these have to be equal, I'm going to need to multiply this equation by 3, because 3 times 2 will give me 6 electrons, and that way I'll have an equal number of electrons lost as I do gained. So that means that 3 times 2 is going to make this 6. 3 is going to get placed here, and then 3 times 2 makes this 6. So let's put together what we have so far. So far, on the left-hand side of the arrows, I have Cr2O7 plus 6 Cl-1. And notice that the electrons are going to cancel because I have 6 on the left and 6 on the right. And so the electrons cancel each other out. So I'm going to combine these two things, and they are going to yield 3Cl2 and 2Cr3 plus. And so I've just kind of combined those two equations, which you'll notice gave me back my original equation, but with the coefficients now in place. Okay, so now we're going to balance the oxygens. Notice we have 7 oxygens on the left-hand side, and so to balance oxygen, we're going to add water. So because I need 7 oxygens on the right-hand side, I'm going to add 7 waters in order to balance this. So notice now I have 7 oxygens on both sides of the equation, and now we have hydrogens that we have to account for. So to balance hydrogens, we're going to add H plus because it's an acidic solution. And so I'm going to have 7 times 2 is 14 H pluses on the right. 14 hydrogens on the right, which means that I need another 14 hydrogens on the left-hand side. 14 H plus. And so now we are totally balanced. We have 14 hydrogens, we have 7 oxygens, we have 2 chromiums, we have 6 chlorines, and we know that we balanced the electrons because we looked at the half reactions up here. And so this would be my final balanced equation for this redox reaction. Example 20.93, balance the following oxidation-reduction reaction that takes place in basic solution, which is going to come with a couple of extra steps from what we did a few moments ago. Let's start by assigning the oxidation states to this lead 4 hydroxide. The chances are not likely that the oxygen and the hydrogen change charges on the left and the right side. So what I want to look at is the fact that hydroxide is an overall -1, and I have 4 hydroxides, which gives me an overall -4 charge here. And so in order for this to equal the 2 negative charge overall, this lead must be a +2, because +2 combined with -4 equals -2. And so I'm going to give this lead a +2 charge. Here, oxygen is a -2, and to be an overall -1, this will have to be a +1. This oxygen is -2. 2 times 2 is 4, so +4 must be what this lead is, and that is telling us it has a -1 charge. So notice our changes. Our lead went from +2 to +4, which is an increase in oxidation state, so it undergoes the process of oxidation, and the chlorine goes from +1 to -1, which is the process of reduction. Now we'll write the half reactions. Remember, in oxidation, we lose electrons, and so that means we're going to write the lead 4 hydroxide yields the lead oxide plus the electrons as a product. And then in reduction, we gain the electrons, and so the electrons are a reactant on the left-hand side. And we have the ClO negative plus some number of electrons yields the Cl minus. Now I need to figure out how many electrons actually transferred in this process. So we have one lead, so an equal number of leads, and the difference between the oxidation states is a difference of 2. 4 and 2 is a difference of 2, times 1 lead equals 2 electrons that were lost. Here, because there's 1 chlorine, and there's a difference between +1 and -1 of 2, on the number line, then that means we had 2 electrons that were gained. Notice that we have an equal number of electrons that are lost and gained, and therefore those will cancel each other out. And so now I can just take these reactants and record them here, and these products and record them here. Now we need to balance the oxygens. We have a total of 4 plus 1 is 5 oxygens on the left-hand side. Put myself a little note there, 5. And on the right side we have 2 oxygens. So I am short 3 oxygens on the product side, which means I'm going to add 3 waters to make up for that. So remember, we balance oxygen with waters. Now I'm going to balance the hydrogens. So I don't need these anymore. We have 4 hydrogens on the left, so I'll put a little 4 there. And we have 3 times 2 is 6 hydrogens on the right. So notice I'm short 2 hydrogens on the left, and I'll balance that with 2H+. So far, we've done what's called balance in acidic solution. However, the question asked us to balance in a basic solution. And so to do that, we're going to now add hydroxides. The point of adding the hydroxides is to neutralize the amount of hydrogens present. So because we have 2 hydrogens, we're going to add 2 hydroxides to the left side, but we also have to add 2 hydroxides to the right side as well. So when I put these hydrogens and hydroxides together, they're going to equal 2 waters on the left-hand side. But notice that I have 3 waters on the right side. So we're going to go ahead and reduce this and say, well, these 2 waters are going to cancel with 2 of these 3 waters, leaving me with just 1 water as a product. And so my final answer would be lead 4 hydroxide plus the ClO minus yields PbO2 plus Cl minus plus 1 water plus 2 hydroxides. Example 20.94, this reaction is an example of a disproportionation reaction where the same atom is being oxidized and reduced. We're going to balance it in basic solution. First, we'll assign the oxidation states. This is going to be neutral. This is going to be negative 2 times 3 is negative 6, which makes this a positive 5. Positive 5, negative 6, make that negative 1. And this is a negative 1. So notice that the bromine goes from 0 to positive 5 here, which is the oxidation part of this reaction, and the bromine goes from 0 to negative 1 here, which is the reduction part of this reaction. So now let's write our half reactions. For the oxidation part, or LEO, remember losing electrons means that electrons are going to be on the product side because they're lost. So we take the Br20 yields the BrO3 negative, where the bromine is a plus 5 charge, plus electrons. And then as the gain electrons for a reduction part of this, we'll put Br20 yields Br negative 1, and notice we're gaining electrons, so I put the electrons on the reactant side. So now, how many electrons have been lost and gained with each of these half reactions? Notice the subscript of 2 here next to bromine means I need a coefficient of 2 here in front of this bromine so that we have 2 bromines on both sides of the equation. The difference between 0 and plus 5 is 5. 5 times 2 equals 10 electrons that were lost. Here we have a subscript of 2, which means to put a coefficient of 2 on the right-hand side. The difference between 0 and negative 1 is 1, and 1 times 2 equals 2 electrons that were gained. We need these two to be equal to one another, so I'm going to multiply this equation times 5, because 5 times 2 is going to give me 10 electrons. So that's going to put a coefficient of 5 here. 5 times 2 makes 10 electrons, and 5 times 2 changes this to 10 bromides. Now I'm going to combine the two equations, and notice that the 10 electrons cancel each other out. And so I'm just going to combine everything that I have left over. Note that we have 1 bromine and 5 bromines, and we're going to actually add those together, which is going to give me 6 bromines here. Yields 2 BrO3 negative plus 10 Br negative. Now we're going to go ahead and balance in acidic solution. Remember, we want to end up in basic solution. So let's start by balancing the oxygens. There are 3 times 2 is 6 oxygens on the right, but 0 oxygens on the left. So I'm going to need 6 waters on the left side to balance that. Now, hydrogen. I have a total of 6 times 2 is 12 hydrogens on the left and none on the right. So I need 12 hydrogens to balance that. That is officially balancing in acidic solution. But we need to go one step further and balance in basic solution. So I'm going to add 12 hydroxides to both sides of the equation in order to neutralize these 12 hydrogens from the acid. So 12 hydroxides. These two are going to combine and form 12 waters. And so I have 12 hydroxide plus 6 waters, 6 bromine, 2 BrO3 negative, 10 Br minus, and these 12 waters. I want to reduce the amount of waters. So these 6 waters are going to cancel with 6 of these 12, leaving me with 6 waters on the right-hand side, which makes my final answer 12 hydroxides plus 6 bromines yields 2 bromate ions plus 10 bromide ions plus 6 waters. So here's the note card, and you can pause the video to copy it down. Leo goes Ger, lose electrons oxidation, gain electrons reduction. You can tell when a loss of electrons occurs if your oxidation state becomes more positive or the oxidation number increases. And if you gain electrons, then the oxidation state becomes more negative, or it decreases or reduces. And if you have the process of oxidation occur, then that must make it the substance a reducing agent. And if it undergoes the process of reduction, it must be an oxidizing agent. If you balance an acidic solution, you're going to assign oxidation states, balance half reactions, then balance oxygens with water, balance hydrogens with H+. If you're going to balance in basic solution, you're going to do all these things, and then you're going to neutralize the hydrogens with hydroxide, adding hydroxide to both sides of the equation, and then you're going to combine the hydrogens and hydroxides to make waters, and then reduce the number of waters in the final equation.